Thank you. Thanks for the opportunity of speaking here. And what I would like to do today is share some of the work that we've been doing in the space of how do we think about controlling networks and, in general, applying control theory in the network space. And the question is, why would we do that in the first place, right? And the reason is that, if you want to think about how would you understand a complex system, like a system with many, many complicated components that interact with each other in some non-trivial fashion, then the understanding has several critical steps. The first, obviously, is that we have to somehow be able to quantify the underlying system we want to study. Once we're able to quantify and build models that describe the system's behavior, we would like to get to the point of predicting some aspects of the system's behavior. And then, and if we succeeded at that, and that could be a very long journey, could be months, years, or often, decades, then you finally find yourself in the position to perhaps control the behavior of that particular system. So I look at control as being one of the ultimate kind of manifestations of your understanding of the system. Now, I'm mindful of the fact that one can control a system even without understanding how it works. There's so-called feedback control that would allow you sometimes to do that. But let's kind of assume that we're trying to achieve something, a first principle-based control, where we really kind of rely on understanding how the system works. Now, the question is, what does it mean to control something or anything, right? And control has many, many meanings in different aspects of human understanding. I mean, there's obviously the idea of controlling something remotely, like controlling a drone, from ground and so on. If you are like one of me who grew up in Eastern Europe or some other system, then control has a bad meaning, right? Of social control and so on. This is not what we're going to be addressing today. What I'm going to do today is that I will be grounding entirely what I'm going to tell you in control theory. And what I mean by that is that, as many of you probably know, among engineers and applied mathematicians, there's a very active field called control theory that has been kind of developing tools and methods and algorithms to control specific engineered systems. And there's a huge literature on that. Many universities have departments focusing entirely on control theory and so on. And others, they are simply part typically of electrical engineering, sometimes of mechanical engineering. So we're going to rely on that literature, and I'm going to highlight just one of the books because this is by Jean-Jacques Slotin, who is one of our collaborators on this particular line of work. We will see his face as we move on. Now, what does it mean to control in an engineering or in the applied math sense of a particular network? And the formal definition is that we say a system is controllable if it can be driven from any initial state to any desired finite state in a finite time, right? So the idea is that if I want to fully describe the system's state, I will have to have a very high dimensional vector or space where I can fully describe it. And I have a control over the system, or the system is underlyingly controllable if I have a way to change its state such that I can get from any initial state to any accessible final state, right? So we're talking about really what are the final states that are accessible. Now, of course, you see, controllability says nothing about how you control the system. It just asks, is it controllable or not? Do you have that possibility? And we'll have to distinguish those things very carefully. Now, to give you a better idea of what this means, let me give a simple example, right? A typical car has about 6,000 components. Yet, when we drive a car, we are not thinking about the state of all the 6,000 components, right? Rather, you have control over 3 or 4 components depending on which side of the ocean you live, right? It's going to be the steering wheel, the gas pedal, and the brake, and the clutch if you are in Europe. And what I'm saying here is that by changing the state of these 3 or 4 components, you are changing the state of the rest of the components. By pushing the gas pedal, you're making the pistons to work faster and so on. And eventually, changing the steering wheel, changing direction. So at the end, the car is built to be controllable from these 3 or 4 components that you have direct access to. And of course, that is so because the engineers, when they designed the car, they made sure that that property is there. So the system is controllable from there, so much so that I urge you never buy a car that would not have those properties, right? But let me go ahead and invert the question. Let me ask the following one. What if I give you a car's wiring diagram? Would you be able to figure out what are the 3 or 4 components from which you can control the rest of the components, right? And you may say that that's kind of a useless exercise because if you bring an engineer in, he or she will be able to tell you right away which are these components. And you would be right on that. But let me say, or let me kind of challenge you on the fact that it's a useless exercise. I think this is what most scientists do day by day in biology labs or neuroscience labs, trying to figure out how their underlying system is being controlled, right? So at the end, the inverse problem is the problem that most of us struggle with. The engineers deal with the direct problem, designing systems that are controllable. In the rest of the sciences, the fundamental sciences, we're dealing with the inverse problem, understanding how a natural system, be that the brain, be that the cell, controls its underlying behavior. So down the line, you know, if you think about what molecular biologists do in the lab when they look at this network, this is the underlying protein-protein interaction network, let's say in a human cell, they're trying to figure out which nodes, which genes do I have to control or change its state such that I can turn, let's say, a sick cell to a normal cell. And you know, about 3 or 4 years ago, the Nobel Prize in Medicine went to a Japanese researcher who discovered 4 genes whose state, if he changed, turned a normal cell into a stem cell. What did he discover? He discovered the 4 control points of the circuit that is controlling the transition from the normal to the stem cell state, right? And so down the line, you know, like even if you're kind of being asked to be in charge of an organization, so this is actually an employees of organization and you know, who is kind of listening to whom, you know, the first question as a leader you have to ask is that who are the people I can rely on to change the culture of that organization? We don't call it a control problem, we call it a leadership problem. But down the line, you would like to know who are the people in the right position in the network through whom I can induce change, right? So that's really the question I would like to address in the remaining time is how would you find out the points from which you can control an arbitrary network? So assume that you have the wiring diagram and you would like to figure out from where we can control that. And this is a work that we started about now 6 years ago with Yang Yu and Jean-Jacques Slotin. And I'll tell you a couple of steps of that all the way to the experimental confirmation that we just obtained a few months ago. So how do we think about control? Well, control fundamentally is not simply a network question. It's a dynamical question because you're trying to control the behavior of the system. So it's unavoidable for us to have 2 things defined when we try to control a system. What is the system, what is the wiring diagram, how the components interact with each other, and what's the dynamics that is defining the state variables on every node in the system. So here's a simple example. I have a small network. Every node has a state variable. That could be the traffic on that node, the concentration of a molecule in a metabolic network, and you name it, whatever your favorite system is. And the wiring diagram is this matrix A, telling me who is connected to whom. Let's assume that it's a directed network. This is A in this case. And then the question I'm asking is that if I'm injecting signal on a selected subset of the nodes, in this case 1 and 2, would I be able to set the state of the other variables in a desired final state, right? Could I control the state of the remaining ones? And here I'm assuming that the network follows, for simplicity, a simple linear dynamics where the state of each variable depends obviously to whom is influencing them, that is the wiring diagram. And then of course this vector B simply tells me what are the nodes that I'm controlling. So just listing the set of nodes that I have direct access to. Now, you can figure it out that if I have access to every single node in the network, then control is easy, right? I set their state to where I want to be, right? But that is not feasible in most systems and not practical either, right? To kind of control each of them individually. So we'd like to ask is that if I only have a subset of nodes, could I control the system from there or not? And the answer actually has been provided by Rudolf Kalman, who is a very prominent applied mathematician and was actually passed away last year, and control theorist, one of the fathers of control theory. And he said, you know, there's actually a simple answer to this question. That is, if you take the matrix A and the vector B and you build what he calls the controllability matrix, and this is how you are building that, right? Then if the rank of the matrix equals with the number of nodes or the number of variables you're trying to control, then you have controllability on that. If, however, the rank is smaller than that particular, than n, then you do not have full control of a system. You can have some partial control, but not full control, right? So it looks like the problem is solved, and let me, before I tell you further, let me just tell you how this works. Just build some intuition about this story, right? So if you would have this little network that you try to control by injecting a signal into node x1 that affects node x2, that affects node x3, and you run the Kalman condition, you would say, yes, this system is controllable, you know, that has rank 3, the matrix, and you know, you could intuitively see that indeed, by taking advantage of the fact that there is some delay between the nodes and so on, you could engineer a signal U1 in a way to set the state of x2 and x3 in an arbitrary position, right? However, if you apply the same logic here, the Kalman condition fails. That is, it tells us that the system is not controllable. And the reason why it does so is because by injecting signal on the top, you're not independently controlling the remaining 2 nodes. Their behavior will be coupled, right? And so therefore, you do not have full control, right? Even though we have the same number of nodes and the same number of things as earlier, you know, this system is not controllable. If you would like to reach control, then you would need one more signal. And if you apply to this network now, the Kalman contract says, yes, it's controllable because I removed this free variable by controlling one more node. Okay? So looks like Kalman has solved the problem in the 1960s, but it didn't. And let me tell you why it didn't. It didn't because, you remember, what the Kalman condition requires is a couple of things that we may not have easy access to. The first is, obviously wants to have a full information about the matrix of how the components are connected to each other. And in most real systems, the weights of the links, for example, are unknown to us, or they are temporally changing, right? So that it could be, you know, time dependent. But that is actually not a problem. The reason why it's not a problem is because there is a whole framework which is called structural control theory within control theory that says, and there's a structural control theorem that makes an amazing claim, and it says, if I'm going to keep the network intact, that I'm keeping the number of links and nodes the way they are, but I assign arbitrary weights to the links, then when I apply the controllability condition, I will get the right answer independent of what weights are applied, except the measure 0 situation where I would get the wrong answer. And I won't get I will get the wrong answer because when I choose the weights in such a peculiar way that some of them actually cancel each other, but that has a measure 0 if I use a real number, so I don't have to worry about that. So down the line, what structural control tells us is that if I want to simply ask if a system is controllable, I do not have to worry about the weights. I can assign arbitrary weights, which we're going to do from now on. But here's the second reason why we have a problem with the Kalman condition. The Kalman condition does not tell you who are the control nodes. All it tells you is that if you have a guess for the control nodes, whether you are right or wrong, right? So at the end, if you would like to find the control nodes, you're going to have to run 2 to the n trials, right? You're going to say, can I control this network from you? Can I do it from you? Can I do it from the 2 of you? And so on, until you find a configuration that actually satisfies the Kalman condition, right? So at the end, you know, if you have a large network, it's impossible to try all of them on. And the third problem, which is equally acute, is that you can't really check the Kalman condition for networks over 1,000 nodes. Because you're going to have to invert matrices of n squared times n, where m is the number of control nodes and n is the number of nodes in the system. And so virtually all linear algebra libraries will fly away with dividing by 0 if you are trying to do that for more than 1,000 nodes. So while in theory it's true, in practice you cannot check whether a large network will actually, whether your configuration is correct, whether the Kalman condition is valid or not. So So this is where we come into the picture. The question is, then how do we figure out what nodes can control the rest of the system? And in particular, what we'd like to ask is that if I give you a network like this, right, which is not too large, it's 300 nodes, right? This is the C. elegans neural network, and I'll talk a little bit later about. Each node is a neuron, and the links are the synapses between them. What we'd like to know is that what is the minimal number of driver nodes through which I can control the rest of the network? How to identify them, right? So one is how many, how do I find them? And eventually, which network characteristics determine that what are these control nodes, right? So in order to answer that, I'm going to ask you to pause now that you're thinking about control and join me in a journey on a completely different mathematical problem that apparently has no relationship to control, but it's a fun problem of its own. And that is the so-called matching problem. A major problem among graph theorists as well as combinatorists. That probably would be approximately right? So, and it's simply, you can be defined in many different ways. The best is the graph theoretic way, and it's a game. One way to define it is to say, I have a network, and I'm going to ask you to label some of the bonds red with the condition that you cannot have two red bonds ending up on the same node, right? And of course, this is a simple situation, and here are some of the red bonds that satisfy that condition. And of course, what I want you to find the maximum matching, which is the maximum number of red bonds I can put into this network such that no two red bonds end on the same node. And tiny network, you can easily figure it out that there's one solution to the top network, and there are three different ways to do it in the bottom network. Matching is a really cool problem. The reason why it's being so much investigated both in graph theory as well as in combinatorics is because it's not only a cool problem, but it has lots of mathematical challenges as well as has very important applications. Matching theory is being used, for example, when medical students apply for residency. That is that the students write down, here is Harvard is number one choice, Yale, Princeton, and so on. So they give you the list of choices where they want to go to do residency. And the hospitals draw a list of choices as well. And then you run a matching algorithm to find the best match such that everybody gets as close as possible to their desires, but everyone eventually gets matched, right? So that's, you are classifying these multiple conditions, right? Your desires as well as making sure the system as a whole is matched. And not only in medical school, actually, in Boston, even the kindergarten placement is decided by a matching algorithm. Parents say, these are the kindergartens I want to send my school, and then, like my kid, and then the kindergartners draw a list, and that also depends on how far you are from that, and eventually run the algorithm. The reason they do that is there are probably too many MIT graduates actually in that neighborhood, so they kind of build the algorithm for them, right? So it's very widely used. Now I'm going to redefine a little bit the matching problem just for going from undirected network to directed network. So here we are, same idea, but the problem is a little bit easier. It's okay to have two red bonds in the same node as long as one is an incoming red bond and the other one is an outgoing one, right? So if I ask what is the maximum matching on these particular networks, you will see that you have multiple cases where one red bond goes in and goes out from the same node, as long as you don't have two red bonds going out or two red bonds going in. Okay, so that's just a tiny modification. And then I'm going to use one language that will be useful for us. The nodes to which a red bond is pointing to, we'll call it match nodes. And those that are not pointing to red bonds, they would call it unmatched, right? So that's going to be what we need. So why did I do this detour into matching theory? And the reason why I did that is because in this particular paper with Yang Liu, we were able to prove a very beautiful and simple theorem. And what that theorem says is that if you want to control a particular network, then the control and the matching problem are equivalent to each other. And in particular, the driver nodes, the nodes that you must control to gain control over the network, are the unmatched nodes of your matching problem on the same network, okay? So I will not prove this theorem. It's in the paper if you would like to do that, to look at it. It intuitively a little bit makes sense. Let's think about it, what it means to control a network and the nodes. Control really requires us to be able to get unique signal to every single node in the system. So the idea is that if a node has a red bond going to it, there is a path taking it, so it gets the signal. And those that don't have one, right, those we need to control to kind of, otherwise they're loose and their behavior is not controlled. So now I'm going to run with this theorem and show you what it means and what we learn from it, okay? And let me tell you what we can do with this. So if you would like to figure out how do I control that particular network that you see over here, then the first step is that you find the maximum matching. Here we go, all right? And then you say everything that is not matched, that is the non-grid nodes, will need to have an input signal to control their behavior, right? And if you look carefully, you would realize that there is not a unique solution to this problem, but there are 3 different ways I can actually put these control signals onto that, because there is a redundancy here on these 3 single connected nodes, right? So degree 1 nodes. So you see actually some of the basic features of what we're going to talk about. Despite the fact that I have 4 different solutions, what is common between them is that the number of nodes I must control is the same, right? So that answers the first question, is that you know, like, even though I have many different ways of controlling the node, there's a fixed number that I need to figure out of how many I need to control. Now, of course, I can always control more, right? But the minimum number is really going to be fixed and unique for a particular network. Now, you may say that I haven't really solved anything, right? Because a matching problem has exactly the same complexity as my original one. I have to make lots of trials if I try to figure out what is my matching for a large network. And if I really do brute force, indeed, I kind of got one complicated problem into another one, not too exciting. But of course, those of you who have been ever exposed to matching, you know that matching is not an complete problem, but there's actually polynomial solution to the problem. There are multiple algorithms that would allow us to find what is the complete match in the system, and we're going to use the Hopcroft-Karp algorithm that has a relatively fast polynomial solution to the problem. And you see it goes like square root of n times L, which allows us to take networks with millions of nodes, and in a few seconds, even in a stronger PC, you can actually find the answer, who are the control nodes in the system. So therefore, the value of this mapping to the matching problem was that we now have an algorithm to identify who are the control nodes of the system, which previously we did not, right? So now we have a tool, right? So let's apply it to lots of large networks, and let's see what we learn from it. And we did it. We put our hands on every single directed network, whether that network is meaningful from a control perspective or not. And then we asked, what fraction of the nodes I need to control in order to control that network? So this is this small nd variable. That is nd equals 1 means I must control every single node individually in order to reach control, right? And it's close to 0, it means that only a tiny fraction of the nodes, if I control, I can go ahead and control the rest of the network. And when we applied it to lots of different type of networks, you see a couple of patterns, right? So first of all, if networks are in the same class, roughly they require the same fraction, like same neighborhood, right? These are regulatory networks within the cell, these are internet-based networks, and so on. Sometimes there are major changes, like in the case of the trust networks, and we'll see why. But the other thing you realize, at least for us, was very counterintuitive, because the regulatory network part of the cell, these are the genes that turn on and off the rest of the cell genes, they are there to control the cellular network. So our expectation was that that should be easily controllable, right? Because its purpose is to control the rest of the system. And yet we find that virtually all of the nodes must be controlled individually in order to control that network. That was unexpected. It was also unexpected that organizational networks require only a few nodes to control them, because we thought that who is the hardest to control? Us, right? We don't want to be controlled, any of us. So therefore, we thought that the social network should be the hardest to control, and yet we found the opposite answer. Which raises the question, what network characteristics determine whether a network is easily controllable or difficult to control? That is, how many nodes I need to control for the network. And there we had an interesting and unexpected numerical observation. And here was the observation. So we said, Let's take an arbitrary network, a real network, for which our algorithm can tell us how many nodes I need to control, right? I already know how to do that. And let me go ahead and randomize that network. What do I mean randomizing? I'll keep the number of nodes and links fixed, but I will completely randomly change who your friends are in that network. In the network science language, I'll take the network and I turn it into an Erdős-Rényi random network, pure Poisson degree distribution. And then we said, let's see how the number of control nodes in the original network relate to the number of control nodes of the randomized network. And this is what I'm showing you here. These are the number of control nodes in the original network. That's the randomized one, and each dot is a different system. I'm showing you what kind of systems we have here. And if it would be the same, it would be along the 45 degrees, right? And for few systems we have them, but for them it's like all over the place. So which makes lots of sense, right? Because I took the network and I turned it into a random network. Your friends are not your old friends any longer. You got completely new friends, so everything has changed. Why would there be a relationship between the original and the new network in terms of how many nodes I need to control in the system? But then we also said, well, we're network theorists, and we know better than assuming that the right randomization is simply to completely turn a network into a random network. The much better randomization is when you do that in a degree-preserving way. That is that if you had many friends in the randomized network, you will continue to have many friends. And if you had only one, you will still have one friend, except that the friend has changed, right? That's what we call degree-preserving randomization, standard tool both in graph theory as well in network science. And we said, let's see how the randomized version, while preserving the degrees, relate to the original one. And voila, it's exactly the same. So that was a purely numerical observation. It was very unexpected, and it's very good news. What does this mean? Well, it meant that I changed your friends, but I kept your degree unchanged. And with that, if I did it for everybody in that network, the number of control nodes didn't change, which means that there's only one variable that determines the number of control nodes in the system, and that is the degree distribution. Right? Because that's the one that I kept invariant. I changed otherwise the matrix, but not the degree distribution. So the number of driver nodes are uniquely determined by the degree distribution. So I don't need to know who your friends are, I just need to know how many you have, and for everyone else. And once you believe that, that is that pay key A in and out, the outgoing and incoming degree distribution uniquely determines the number of driver nodes, then we can do math. Actually, we could turn to spin glass theory, and in particular the cavity method, and effectively look at many realizations of the same network with the same degree distribution, and ask ourselves, what would be the expected number of driver nodes, and gave us a mechanism through which to calculate using cavity method the number of driver nodes in the system. And this is exactly what we did. So for example, in the Erdős-Rényi, the calculation predicted that the number of driver nodes decreases exponentially with the average degree of the network. That is, the denser the network is, fewer driver nodes in the system. And this is the numerical evidence. I'm showing the number of driver nodes for a model versus the average degree. And you see that it decreases exponentially. And when you look at the scale-free network, the same story, except the exponent depends on the degree exponent as well. So the decay rate is modulated by the degree exponent of the underlying scale-free network. So therefore, denser networks are much easier to control than less dense networks. And that is because in the denser networks, I have multiple paths to get from one node to the other one. And therefore, I have multiple ways of sending a unique signal to the system. We also asked, how does degree heterogeneity affect the number of driver nodes? And degree heterogeneity kind of asks that if I have a square lattice, I have no degree heterogeneity, right? Because each node has the same degree. I can have a random regular network where nodes are randomly connected, but everybody has the same degree. That's still zero degree heterogeneity. And of course, the most heterogeneous case where you have one node connecting to everyone else because you have one huge hub and many small nodes. So the Gini coefficient allows us to measure that, and what we find is that the more heterogeneous the network is, the more driver nodes you need to control. That is, the more hubs are in the system, the harder it is to control that system, which was unexpected, right? Because we thought the hubs are the controllers, right? So they're the master controllers. But it's not the case because the hubs typically means that there are lots of dangling points, and all of these dangling points have to be individually controlled if there's a hub in the system, right? So that's, so down the line, when we put the pieces together, what we found is that the mean degree and the heterogeneity are two factors that determine the number of driver nodes. And the interesting thing is that it turns out that sparse and heterogeneous networks are harder to control than dense and homogeneous networks. And the reason why this was surprising to us is because most real networks are sparse and heterogeneous, right? So they're exactly in the territory that are harder to control. So somehow nature prefers those networks that require many control nodes rather than a few. Now, let me just walk you over what happened. What was the magic that I did here? Because there were jumps that I did. So I said, you start with an arbitrarily weighted network, and then we're going to move to structural control, to the structural control theorem, and I'm going to work with you in a binary network. I don't care about the weights, right? And then I used the matching theorem, right, the maximum matching theorem, that allowed us to kind of identify what are the driver nodes, so that by mapping the control problem into a matching problem. And there the arrows end because the next step is not proven. It was a numerical observation that the degree distribution determines the number of driver nodes. No one has been yet able to prove that. I talked with several mathematicians that it's very plausible, probably very difficult to prove, but it feels right. But once you accept that, then we can use the cavity method to calculate analytically or write down an equation for the number of driver nodes. And in some limits, you can actually get some limiting results, and then you get results like how the number of driver nodes depend on the average degree or some other variables, okay? So that was the magic that we did. I want to show you this so that you understand that there's actually a lack of arrow here, that we cannot kind of connect the unmatched driver nodes directly to the degree distribution. That was numerically observed. Now, what I want to do in the remaining few minutes is just to tell you a little bit about that this is not only theory, but we have actually experimental evidence that it works. And we've been working for 5 or 6 years on the problem, and I've been really pushing my lab. We need to find a proof of principle that this is really valuable in real systems. And eventually, we ended up focusing on the C. elegans neural network. The reason we did that is because that's the only organisms for which we have a very well-mapped, relatively well-mapped neural network, so we know what are the nodes and the links in the system. And in particular, we're going to focus on a particular behavioral pattern, which is what the C. elegans does when you touch it. And that's what you see in this particular video. First, the C. elegans comes to the left, then we touch it now, and then it turns around. So this means that it does two things. It senses the fact that it has been touched, right? And then once it's sensed, then it sends a signal and it reverses direction. So it changes the motion of the muscles, right? So that it will start running away from the touch, right? It doesn't like to be touched, so it goes away, right? And biologists have worked, neuroscientists have worked a lot on these particular organisms, and they would tell you it does so by using the following steps. So you have some neurons, sensory neurons, and then they transmit information to these neurons, and eventually through them the information gets to the muscles. And to give you an idea, the muscles are all over along the body. So down the line, if you, so they would tell you, and rightly so, that the mechanism through which this happens is understood. We know the pathways and the neurons involved in the process. And these are the neurons involved in the process. So, so then the question we would have is that how do we know that? Well, the way they know that is because they have knocked out each of them individually, each of these neurons that they sense to be part of it, and they realize that if one of them is missing on this list, then either the animal doesn't turn around, doesn't seem to sense it, or it just ignores it, or it doesn't do the motion right. So it limps, it works in a funny way. So, and effectively down the line, there is quite a bit of experimental evidence, and this is the list of neurons whose individual ablation, which is kind of removal from the animal, has certain experimental consequences that makes us believe that for that reason they are part of that particular process. Now, there's only one problem with this beautiful explanation. It makes you believe that it is that simple as input goes to the output through these few nodes. When you actually look at the network, you're seeing this, right? There is no separate pathway. These big yellow nodes are those that were over there, and they are fully integrated with dozens of connections to other nodes that have no relationship to the motion based on our experimental evidence. So the question is, could we start from this network without experiments and tell you which of the nodes are responsible for control, right? Because we could pose this one as fundamentally a control problem. Can the inputs, which are the sensory nodes, control the muscles, right? And in order to pose that problem that way, we're going to use one particular result that we had earlier, kind of a generalization of the earlier result, and is to say that if I have a set of nodes that is trying to control a layer of nodes underneath, the system is controllable only if the number of nodes on the top is larger than the number of nodes in the bottom. If it's the other way around, the fewer nodes are trying to control more nodes, you do not have full control over the bottom layer. This is equivalent to, the one node trying to control two nodes, right? The generalization of that, one of them is going to be loose. Generally, if you have fewer towards more, you don't have full control over the system. So let's apply that to the neural network, and this is what you get. It's a little bit messy, but eventually what you're trying to do is to say, hey, can these two input nodes where the sensing is happening control the muscles, which are these purple guys? And the answer is, well, they can't. And the reason why they can't is because at the top layer, we have 9 nodes that directly control the bottom layer, and it's underdefined, right? So you have fewer nodes trying to control more nodes, and you do not have full control over the muscles. But that's all right, because I don't need to control every single muscle of mine to actually individually to move my hand. There could be lots of correlations between them, right? So it's perfectly okay for them to be moving together. And that's what we see in the C elegans as well. You do not have complete control over the muscles, and the system can exist with that. But here's the question I'm going to ask. What if I remove a node? Will that change how many nodes I have to control? And in this case, actually, the DD network, DD nodes, is one of them that is known to affect controllability. And if I'm going to knock this out, that is remove it from the network, and I redo my control analysis, I find that, of course, the layer goes from 9 to 8, and in this case, the number of controllable muscles goes from 15 to 14. So I lost some degree of control, okay? That could be a problem. So we said, we have 300 neurons in the C. elegans neural network. Let us do this calculation for every single of them. And this is where the magic happened. Out of the 300-something neurons, only 11 of them had that property. That if you remove them, then we lost some control over the muscles. The rest of them, you could remove it, and there was no change in how many muscles you are able to control. And we said, oh my goodness, this is way too small. We're either completely wrong or we're completely right. So we started looking into literature, and it turned out that everything that was in the list we recovered through this methodology. So control told us exactly everything that the biologists over 30 years of experimentation that discovered about who are the muscles, or who are the neurons that are involved in the control without doing a single experiment on our end. And the method also told us that there is one more that they didn't know about it. And that was the so-called PDB. And the reason why they didn't know about it is because all these other neurons are not single neurons, but neural classes. There are multiple copies of them. And PDB is a single neuron. And somehow they had some intuition that these neural classes are responsible, so they knocked them down as classes, and they never bothered to knock it down, the PDB. But our methodology said that too. So why is that first? Well, it is because if you're going to, this is PDB here, and if you knock it out, then the number of controllable muscles go from 7 to 8. So according to our criteria, we lose some degree of control. And so what we did is that we started talking to people who can do this type of experiments, and the group in Cambridge, UK actually was able to do that, and they did, and the evidence was exactly what we predicted. In a sense that what you see here in the experimental language is that the animal that was missing that particular neuron was not walking right, which is the experimental evidence that is actually, its motoric functions are perturbed. Same type of evidence based on the other neurons were actually discovered. So here's the beauty. This particular was kind of verified by the experiments. But I have one more, I can probably, well, actually, we had one more prediction. I told you that all these other classes were classes of neurons. So DD class, for example, made of multiple neurons. And we said in the class of neurons, only some of them are responsible for the effect. And for example, we said the DD1, 2, 3 are not, but the DD4, 5, 6 are responsible. If you individually knock it out, you will see that. That hasn't been done before. Our collaborators did that, and we were exactly right. When they knocked out these guys, there was no effect. When they knocked out these guys individually, the animal was limping. Let me show you what it means limping. This is the healthy one, right? It kind of goes nicely. And this is the one that is missing, I believe, one of the DDs, DD4, the DD5, you see. And what you notice there, and of course they're able to, they measure about 4,000 parameters on this motion, kind of from the videos, is that it's dragging its back. So its back is not really curving, but it's being dragged after that. The front is moving normally, but the back is being dragged. So lost control over the back muscles. So let me just kind of conclude is that the magic of the control here really is that we were able to predict precisely, not just give you a rank list that this is most likely most involved and this is the least involved, but we were able to, the control tools told us exactly which are the nodes involved in the control. And we were, I wouldn't say we're lucky enough, but we're actually exactly on the money because I think there's more than luck involved in this particular process. And so given that I'm out of time, I'm just going to jump to the contributions who have made this happen. This is the team actually who worked us originally on the control tools, so Jean-Jacques and Yang-Yu Liu, and they were the one who worked out the theory for the C elegans, and this is the experimental team actually who did the experiments, and we're really delighted about the fact that we finally have a proof of principle that control tools are really applicable in biological systems. And I believe that this is just the beginning of a story, right? We will find that when we look at cell biology as well as brain, control is fundamental for this system's ability to exist and function, and we will have to use this type or other type of control tools to unveil how these systems work. Thank you very much for your attention. Sure. This is obviously, I'm so glad you asked because I'm sure many of you were thinking the same thing. So you see, the question we're asking is to what degree the topology affects controllability. And there is no general theory of nonlinear control. So there is no such a thing as Kalman condition. But what the nonlinear control community knows, and I've been told by them and taught by them, is that even if you have a nonlinear system, the nodes that the linear control predicts will continue to be control nodes. But because in nonlinear systems, some of the modes die out naturally, you may not need all of them. So they effectively say, guaranteed that those that you are finding through the linear theory will allow you control, but you may be overshooting. So that's the approximation we're using. There has been recently a number of papers that have tested that in the sense that they looked, for example, at both brain models and other things, and what they found is that indeed this gives a very good approximation in a non. So if you use this one that you get from the linear theory and you try to control the system, then you're pretty much at your money.
What about like time varying?
That's a beautiful question. We have a paper just accepted in Science. We're very excited about time-dependent networks, and here is the unexpected result. Why is this a science paper? Time-varying networks, those that wiring diagram is changing, are orders of magnitude easier to control than the fixed networks. And to give you intuition, why is that? Is because one of the things that I didn't talk about it is the control energy, how much efforts I need to put in to control the system go in a certain direction. And we have a set of results to show that there are orders of magnitude difference depending on which direction in the phase space you want to go. And what I mean orders of magnitude is that could be 100 order of magnitude more expensive to go in this way than going that way. In a time-varying network, the network is always changing. So therefore, if I want to go there, I just have to wait a little until the network changes so it's not going to be so expensive, and then I can do that. So it's a little bit like sailing in a non-fixed wind, right? I put up my sails or put it down so that I go in that direction, and I'm not trying to go against the wind. So it turns out that in time-varying networks, you need typically fewer or equal number of control nodes. You need many, many times less order of magnitude energy to obtain control, and the control trajectories are much shorter in the phase space than those that we do in the fixed network. So that may be one of the reasons why so many complex systems actually do employ time-varying networks. The simple example I like to give is that if the car would not be a time-varying network, it would be really difficult to park, right? Because the reason why you can park is you can go forward, backward, right? And if you wouldn't have that, try parking on Harvard Square. Right? Thank you.